So in this problem, we're given a cannon of mass m that is shooting a cannonball of mass little m and is attached to a spring of force constant k that compresses sub delta x when the cannonball is fired. Now your first thought may be to simply conserve energy from the cannonball to the spring and just finish it there. But that's actually not the correct way to do this, because the cannon actually needs to recoil and thus is also going to have energy during this process. So what we actually need to do is we have to conserve energy from the spring to the cannon, because it's the cannon that's actually pushing against the spring. And then once we find that, we can find the initial velocity, the recoil velocity of the cannon, and we can use that to conserve momentum between the cannon and the cannonball. So, in order to conserve energy, we take E initial equals E final. E initial is the kinetic energy of the cannon. That's going to be 1 over 2 mv squared. I'm going to use big V to denote the initial velocity of the cannon, is equal to 1 over 2 k delta x squared. So now we're trying to solve for V. We get V squared is equal to k over m times delta x squared. And big V, the speed, is equal to the square root of k over m times delta x. Now, all we need to do is conserve momentum from the cannon to the cannonball. And we're going to do that with P initial is equal to P final. We're going to define this direction to be positive, the x-hat direction. And so P initial is going to simply be 0, because the cannon and the cannonball start at rest. P final is going to be little m times little v vector, so that's the momentum of the cannonball, plus big M times big V vector, that's the momentum of the cannon. Now this plus is very important. When you're conserving momentum, we're actually adding these vectors together. So afterwards, once we take out the speeds, this is going to be negative because it's pointing in the other direction as cannonball. The cannonball is moving in the positive x-hat direction, the cannon is moving in the negative x-hat direction. But right now, it's really important that we add them together. So this gives us m v vector is equal to minus big M, big V vector. V is equal to minus big M over little m times V is equal to minus big M over m times root k over m delta x times minus x hat. So this here is the speed, big V, and this is the direction of the vector. So now we can take these two minuses and cancel them out, and cancel out the square root of m with that, and we get root k big M over little m times delta x, x hat. And so that's going to be our final velocity. Now, our initial velocity for the cannonball. Now in the problem, we're given actual values for these. So we're given k is equal to 20,000 newtons per meter. Big M is 200 kilograms. Little m is 10 kilograms. And delta x is 50 centimeters, or 0.5 meters. Now plugging those in, we can get the initial velocity is equal to 20,000 times 200, and that's going to be in units of kilogram newtons per meter, divided by 10 kilograms times 0.5 meters in the x-hat direction. And when you do all the math and work out the units, this works out to be 100 meters per second in the x-hat direction.